Let's consider the behaviors of processes. Bursts of CPU usage alternate with periods of waiting for I/O. This is a CPU burst, then comes waiting for I/O and doing I/O operation. Another CPU burst, I/O operation, CPU burst, I/O operation, CPU burst, for example. In part A CPU-bound process is given. We have relatively long CPU bursts. This one is an I/O-bound process. We have several short CPU bursts. If we consider batch systems, there is often more processes submitted than the number of processes that can be executed immediately. Hence, incoming processes are spooled to a disk. The long-term scheduler selects processes from this process pool and loads selected processes into memory for execution. Short-term scheduler selects the processes to get the CPU from among the processes which are already in memory. Short-term scheduler executes frequently, mostly at least once every 10 milliseconds. It executes on CPU and has to be very fast. If it takes 1 millisecond to choose a process, this means 1 over 10 plus 1, which is equal to 9% of the processor time is being used for short-term scheduling, and only 91% may be used by user processes for execution. Long-term scheduler, on the other hand, executes much less frequently. It controls the degree of multiprogramming, that is, number of processes in memory at a time. If the degree of multiprogramming is to be kept stable, say 10 processes at a time, then the long-term scheduler may only need to be invoked when a process finishes execution. Time-sharing systems mostly have no long-term scheduler. The stability of these systems either depends upon a physical limitation, for example, number of available terminals, or the self-adjusting nature of user. If you can't get response, you quit. It can sometimes be good to reduce the degree of multiprogramming by removing processes from memory and storing them on disk. These processes can then be reintroduced into memory by the medium-term scheduler. This operation is also known as swapping. Swapping may be necessary to improve process mix or to free memory. Categories of scheduling algorithms are as follows: 1. Batch, 2. Interactive, 3. Real-time. Performance criteria. In order to achieve an efficient processor management, operating system tries to select the most appropriate processes from the ready queue. For selection, the relative importance of the following may be considered as performance criteria. For all systems, fairness, given each process a fair share of the CPU. Policy enforcement, seeing that stated policy is carried out. Balance, keeping all parts of the system busy. For the batch systems, throughput, maximize jobs per hour. Turnaround time, minimize time between submission and termination. CPU utilization, keep the CPU busy all the time. For interactive systems, response time, respond to requests quickly. Proportionality, meet users' expectations. For real-time systems, meeting deadlines, avoid losing data. Predictability, avoid quality degradation in multimedia systems. Some goals of the scheduling algorithms under different circumstances are listed here. The value of the mentioned performance criteria are calculated as follows. Processor utilization. This is the ratio of busy time of the processor to total time. It is calculated as processor utilization is equal to processor busy time divided by processor busy time plus processor idle time. We would like to keep the processor as busy as possible. Throughput. This is the measure of work done in a unit time interval. Throughput is calculated as number of processes completed divided by total time. Turnaround time. Turnaround time is the sum of the time spent in the ready queue, execution time, and I/O time. Turnaround time is calculated as the time process completed minus the time process submitted. Waiting time, WT, time spent only in ready queue. Processor scheduling algorithms only affect the time spent waiting in the ready queue. Hence, considering only waiting time instead of turnaround time is generally sufficient. Response time, RT, the amount of time it takes to start responding to a request. This criterion is important for interactive systems. Response time is the time that first response of the system occurs minus the time at which the request is submitted. The first response corresponds to the time that the process starts execution. We normally want to maximize processor utilization and throughput and minimize turnaround time, waiting time, and response time. Sometimes other combinations may also be considered depending on system requirements. For example, for time-sharing systems, response time is quite important. The algorithms for scheduling in batch systems are as follows. First come, first served, shortest job first, shortest remaining time next. The goal of a scheduling algorithm is to select the most appropriate process in the ready queue. For simplicity, we will assume that we have a single I/O server and a single device queue. Device queue always implemented with first come first served, which is also called first in first out method. We also will neglect switching time between processes, context switching. First come first served algorithm. First come first served may cause processes with short processor bursts to wait for a long time. If one process with a long processor burst get the processor, all the others will wait for it to release it and the ready queue will be crowded. This is called the convoy effect. We will consider the following processes and will apply different scheduling algorithms on it. We have 4 processes. In this column, their arrival time is given. A arrives at 0, B at 2, C at 3, and D at 7. Each process has a sequence of execution burst and I/O burst. For example, for A, we have execution, I/O, and execution. For B, we have only execution, I/O, and then execution. For process A, the time required for the execution of the first burst is 4 units. Then comes I/O, it is 4 units. Then the second execution, second CPU burst is 4 units. Second I/O is 4 units. And third execution burst is 4 units. In fact, without executing the processes, we cannot know what is the required time. However, here, to compare the algorithms, we assume that we know the time required for each execution and I/O burst. For process B, the first execution requires 8 units of times, first I/O requires 1 unit of time, and the second execution requires 8 units of times. For process C, we have timing as 2, 1, 2. Then process B and process C finishes after second execution. For D, we have execution and CPU burst as 1 unit of time for each other, and execution, I/O, execution, I/O, and execution. If we compare the process B and D, the total time required for process B is 17 units of time, and for process D, it is 5 units of time. If we compare these two, B is a CPU-bound process, and D is an I/O-bound process. The others are between them. First, we will consider first come, first served algorithm. It is shortly called FCFS. In this algorithm, the processes to be selected is processes which request the processor first. This is the process whose process control block is at the head of the ready queue. In the system, we have a ready queue in which we have the processes which are ready for the execution, but they are not executing because the processor is busy for the execution of some another process. And similar to ready queue, we have a queue for each input-output device. Contrary to its simplicity, its performance may often be poor compared to other algorithms. First come, first served may cause processes with short processor bursts to wait for a long time. If one process with a long processor burst gets the processor, all the others will wait for it to release it, and the ready queue will be crowded. This is called the convoy effect. Here the Gantt charts for CPU and I/O are given for the execution of the processes that we considered previously, for the execution of the processes A, B, C, and D, for which the arrival time and also the length of the execution and I/O bursts were given previously. Process A arrives at time 0 and enters the ready queue. Because the ready queue was empty initially, this is the first process in the queue, and because the CPU is idle, this process is chosen for execution immediately. So it is removed from the ready queue and it starts its first execution. The first execution is 4 units of time. Before the first execution of process A finished, process B arrives to the system at time 2. It enters to the ready queue. It waits there because process A is executing. Meanwhile, process A continues its execution. Again, before the first execution of the process A finishes, process C arrives to the system and enters to the ready queue. There were process B previously in the ready queue, then after that process C is inserted. Here it is shown that process C submitted to the system. A continues its execution. At time 4, the first execution of process A is completed. Process A leaves CPU and enters the I/O device queue. Because the I/O device is idle, it is immediately chosen for the I/O operation. The first process in the ready queue was process B, so B starts its first execution. While process B continues its execution, process D arrives to the system. It is inserted to the ready queue. B continues its first execution and A continues its first I/O operation. At time 8, the first I/O of A is completed. So it enters back to the ready queue. B continues its execution. There is no process waiting in the I/O device queue, so I/O device becomes idle. It was also idle here in the beginning. At time 12, the first execution of process B terminates. It enters the device queue and starts I/O operation immediately. Process C is the one in the front of the ready queue. It is deleted from the ready queue and process C starts its first execution. This is the first I/O operation of process B and this is the first execution of process C. At time 13, process B finishes I/O operation and enters the ready queue. At 14, the first execution of process C finishes. It goes to the device queue and the process in the front of the ready queue is D. D starts its execution. This is the first execution of process D. At 15, D finishes execution. It goes to the device queue. Meanwhile, C finished its I/O operation. It enters the ready queue. At time 15, D finishes its execution and it goes to the device queue. Meanwhile, process C finishes its I/O operation. It enters the ready queue. The first process in the ready queue is process A, so A is chosen for the execution. This is the second CPU burst of the process A. At time 16, D finishes its I/O operation and enters back to the ready queue. At time 19, A finishes its second execution. It goes to the device queue and starts immediately to the I/O operation. The first process in the ready queue is process B. B starts its second execution. At time 23, process A finishes its I/O operation and enters the ready queue once more. B continues its execution. At 27, process B finishes the second execution. And this is the last CPU burst of the process B. There is no other operation after that. B terminates and leaves the system. The first process in the ready queue is process C, and it is chosen for execution. At time 29, process C finishes its second execution. There is no more operation, so C terminates and leaves the system. At time 30, D finishes the second execution and enters the I/O device queue. Because it is empty, it immediately starts its I/O operation. Meanwhile, the process A is the only one in the ready queue. It is chosen for execution. This is the third execution of the process A. At time 31, D enters to the ready queue, and at time 34, the third execution of the process A finishes. So process A terminates and leaves the system. D is the only one in the ready queue, so it is chosen for execution. This is the third execution of process D. At time 35, D completes its third execution and D terminates, it leaves the system. The total time required for all the processes to complete their operations is 35 units of time. And notice that all the time the processor is busy. Processor utilization is processor busy divided by total time multiplied by 100. It is 100%. Throughput is we have 4 processes completed. The total time is 35. So throughput is 0.11. Turnaround time for process A is calculated. The time process A terminates, which is 34, minus the time process A submitted to the system. So the difference is 34. For process B, it is submitted to the system at time 2 and it completes its operations at 27. It terminates at that time. So turnaround time B is 27 minus 2, which is 25. And similarly for the process C terminates at 29 minus the time it is submitted is 3. The difference is 26. For process D, it terminates at 35 and it was submitted to the system at 7. So the difference is 28. For the calculation of the turnaround time average, we sum all these turnaround times and the sum is divided by the number of processes, which is 4. So average turnaround time is 28.25. For the calculation of the waiting time, we have to consider the time spent in the ready queue. For the calculation of waiting time for process A, we are considering at which times the process enters the ready queue. It enters the ready queue 3 times. Its first entrance to the ready queue is when the process A is submitted to the system. The second one is when the process A finishes its first I/O operation, then it enters the ready queue. And the third one is when the process A finishes its second I/O and then it enters the ready queue. For the first entrance, process A is chosen immediately from the ready queue and it starts execution. So the difference is 0 minus 0. For the second one, It enters the ready queue at 8 and it is chosen for execution at 15. The difference is 15 minus 8 plus for the third one, it enters the ready queue at 23 and it is chosen from the ready queue at time 30. The difference is 30 minus 23. So if you consider all these terms, the waiting time for process A is 14. The waiting time for process B is similarly calculated. It enters the ready queue at 2. It is chosen for execution at time 4. So the first term is 4 minus 2. Here A finishes its first I/O and enters the ready queue the second time. It is chosen for execution at 19. So the difference is 19 minus 13. If you consider all the terms, the total is 8. For process C, it enters the ready queue at 3 and it is chosen for execution at 12. So we have 12 minus 3. It enters the second time at 15 and terminates at 27. So we have the term 27 minus 15. When we consider all these terms, the total is 21. For process D, it enters the ready queue 3 times. This is the first entrance. And at 14, it is chosen for execution. We have 14 minus 7. The second one starts at time 16. It waits there until 29. So we have 29 minus 16. The last time, it enters the ready queue here at 31. It's chosen for execution at 34. So we have 34 minus 31. When all these terms are summed up, we have 23. The average waiting time is the average of the waiting times given here, which is equal to 16.5. Notice that the average waiting time is less than the average turnaround time because waiting time considers only the time spent in the ready queue, while turnaround times consider all the time spent either in the ready queue or while they are executing or while they are doing I/O operation. As the response time, we consider the difference between the time process submitted to the system and the time at which the process starts its execution. The process A enters the system at time 0 and it immediately starts its execution. Because of that, the response time is 0 minus 0. It is equal to 0. The process B enters to the system at time 2. It starts its first execution at time 4. The difference is 4 minus 2. So the response time for process B is 2. The process C enters to the system at time 3. Its first execution starts at 12. So the difference is 12 minus 3, it is 9. The process D arrives to the system at time 7. It starts its first execution at 14. The difference is 14 minus 7, so it has response time as 7. When the average of these response times is calculated, it is equal to 4.5.